Well, a very good afternoon to you, if you are indeed in the afternoon, as I am. I am calling you from Hobart. My name is Kate Robertson. I'm the Executive Director of Advancement, and I'm bringing this webinar to you from the Sandy Bay campus today. We are very pleased to be able to host this online series for our alumni, Explore, and it's good to see so many people on the call. And I can see even as we speak, the numbers are rapidly going up. So a very warm welcome to you, wherever you may be at the moment. Firstly, as a reflection of the institution's recognition of the deep history and culture of this island, the University of Tasmania wishes to acknowledge the traditional owners, the Palawa people and custodians of the land upon which we meet. And we pay respect to elders past, present and emerging. This series, Explore, provides a wonderful opportunity that we've designed specifically for our alumni community. And the idea really is that for graduates of the University of Tasmania, we provide a really wonderful opportunity for enrichment and advancement and inspiration, really drawing on the wonderful expertise and access we have to our global community. This series, apart from providing you with insights and knowledge and inspiration, allows you also to connect with alumni around the world. And that we hope that being part of this program, and indeed today's webinar, you find sources of new inspiration, new knowledge, and perhaps even some new friends and new networks. Maybe there's some potential collaborators amongst you. So the idea is that you learn, you listen, you engage, you meet new people. So a very warm welcome to you. There are just a few housekeeping rules. I know a number of you will have joined this webinar series several times, but for those of you who are new, and before the conversation gets underway, just to let you know that the microphone, camera and chat function, as well as the raised hand functions, have all been disabled, and that's so that our speaker is not interrupted during his presentation. But we do encourage you to think of questions as we go, and indeed to ask questions, and you can do that using the Q&A function on Zoom. So you can see that at the bottom of your screen where it says Q&A. Just pop the question in there at any time during the presentation and we will come back to that. Now, sometimes we do find that we get a lot of questions and quite a few of them can be similar. So as the host today, I will do my best to curate and facilitate the questions as best as I can to get through all the inquiries that you might have. If you're asking questions that are of a very highly personal or particularly medical nature, again, we'll take the liberty to find an appropriate way to ensure that we're asking questions that have the broadest interest to all of the people on our session today. But today, we're very lucky to be joined by alumnus and co-founder, president and chief investments officer of Life Biosciences. Aging is the biggest risk factor for almost every chronic disease. And we can tell by the popularity of our session that it's something that's of keen interest to our alumni community. Today, we will hear insights into the groundbreaking research over the past decade that has shown that aging is a modifiable risk factor that can be targeted therapeutically. I'm sure we'll be very pleased to hear more about that. So it gives me great pleasure to introduce to you our speaker, Tristan Edwards. Tristan is a graduate from UTAS. He studied Bachelor of Commerce and graduated in 1997. So we're very pleased to have him with us. And I should point out that Tristan is actually on business in the States at the moment. He's in Boston, so he's actually making this call from the early hours of, well, late 11 o'clock at night, I think, coming into midnight. So we very much appreciate Tristan taking the time to be with us at this inconvenient hour. Tristan has extensive global financial capital markets, regulatory compliance and fiduciary oversight experience, following a 16-year investment career spanning leading financial organisations across Australia, London, Hong Kong and Singapore. Having recognised the opportunity to leverage this experience in entrepreneurial environment, He has subsequently moved to pursue his passion for helping create a scalable platform for financing and enabling the world's best scientists and thought leaders to create change. So we extend a very warm welcome to Tristan, and I'm now going to hand over you to begin your presentation.
Thank you, Kate. As Kate mentioned, my background is finance, not science, so I'll keep this presentation fairly high level. I spent most of my career as a hedge fund trader, trading equities, and I've always had a long-term interest in the idea of aging research and the idea that age is hackable and that the mechanisms of aging can be understood and even reversed one day. And in early 2016, I was watching the science and thought it had advanced enough to be at a point where it was no longer science fiction and we could raise money around longevity research. So this is what I did. I moved to Boston, pulled together the best aging scientists I could find. My partner was Dr. David Sinclair, who you may have heard of. He's also Australian, but he's been living in Boston for, I think, nearly 20 years. He runs the aging lab at Harvard. And we pulled a lot of IP out of Harvard, out of Einstein University, UCLA, UNSW in Sydney, Virginia Tech, and really just did a land grab on all the best aging IP we could find globally in early 2016 at a time when most people from the finance industry weren't thinking about this. There was no obvious path to liquidity. This was something we were doing really because we were outcomes focused. And we were just very fortunate that the space took off as quickly as it did. I'm going to share my screen and take you through a quick presentation. Now, I can't show you too much because a lot of this stuff is confidential, but I'll show you some high-level ideas anyway, and there's still plenty here that we can talk about. So Life Biosciences is a Boston-based biotech, and the company focuses exclusively on aging research. And when you think about aging research, there are, I guess, two ways to think about it. The landscape at the time when we started this company was one of healthcare extension. So if you can extend your health span extension, if you can extend your health span, you will also extend your lifespan. But it's really about extending quality of life. You don't want to extend age just for the sake of extending age if the extension is poor quality of life. And so we have molecules today that we think can get humans to 120, and the humans will be in perfect health. They'll be in better health than probably most 60-year-olds are today. And then rather than having 10 years of decline at the end, they'll have 6 months of age compression, mitochondrial exhaustion, and they'll just stop. So it's an ultimate aging model. So that's one area of focus with longevity research is removing aging diseases and extending health span, which will also then extend lifespan. The other area of aging research is age reversal, which wasn't possible when we started this company, but has become possible in the last 2 years. And our age reversal science actually made the front cover of Nature last year, which was a big milestone for us, but I'll come to that in a moment. Why can't I move my page? There we go. So I describe this company as the world's first real healthcare company. And I say that because every other biotech or pharmaceutical company out there is a sick care company. They wait till you get sick and they try and treat your symptoms in a reactive way by treating downstream symptoms of aging. And it's not a criticism, it just hasn't been possible to treat upstream causes of aging before. So, for example, cardiovascular medicine won't help Alzheimer's. Type 2 diabetes treatment won't help dementia or cardiovascular or cancer. So each aging symptom has its own specific disease state and has its own specific treatment to try and treat those diseases. But if you go upstream and treat causes of aging, one molecule can treat multiple downstream symptoms collectively, which makes intuitive sense, both in a reactive way and in a preemptive way. So if we'd met in the 1920s, the average lifespan for humans was 39. And that statistic is skewed by child mortality, but most humans back then were dying from infection. They weren't living long enough to get aging diseases. Some were, but most were not. And then we discovered penicillin, and with antibiotics, we remove infection as a risk, and we start pushing into this space of aging diseases. And now the average age for humans is 79. But of that 40-year increase in lifespan, only 20 years was an increase in health span. The other 20 years was sick span. And so now we spend 10 to 15 years in decline. What we're talking about now is adding another 40 years to lifespan and getting humans to 120. But of that 40-year increase, 39 years will be a health span, and will compress 6 span from 10 years down to 6 months. And so you'll be healthy, 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 and then mitochondrial exhaustion, and your body will just stop. And that's the technology we have today going through the FDA. This should be available in 5 to 7 years' time. And I guess one way to think about this is, if we cured all cancer today, you would only add 1.6 years to average lifespan, because there are so many other aging diseases waiting to get you. So really, the only way to kind of push past this barrier is to remove aging diseases collectively by treating aging itself. So what do I mean when I say treat aging? So there are, depending on how you measure, there are between 7 and 9 aging pathways. We identify 8. Europeans identify 9. Americans identify 7. We all agree on the landscape. It's just semantics on how you slice up the different indications. And through treating these aging pathways, you remove those barriers I was just showing you. So you'll live a longer, healthier life, but you still grow old. Just grow old in a very healthy way, and you end up living longer because there's nothing there to stop you. And our company started focusing on each of the 8. And then as we got into the science, we realized that some of this stuff was too early and wasn't ready to be commercialized. And so we focused on 3. And I'll take you through those 3 now. These are the 3 here. 2 of them are in the first bracket of health span extension, and the third one is actual age reversal. So these are the 3. So mitochondrial uncoupling. So a good way to think about this is metabolism. So you may have heard that one way to increase your health span and your lifespan is through aggressive fasting, calorie restriction. But the amount of calorie restriction you'd need to endure to have a meaningful impact on your lifespan is really too hard for anyone to tolerate. So we're making molecules that mimic the same calorie restriction pathways, which makes you live longer. But what it's really doing is it's restoring youthful function to your metabolism. So it treats all the diseases that come with an aged metabolism. So a way to think about it is, imagine, say, a 75-year-old human. With that age, often it comes weight gain. It's harder to keep weight down as you get older. So the 75-year-old human is probably obese, has type 2 diabetes, has fatty liver, and has Nash. All 4 diseases come from the same cause. It's ultimately aging, an aged metabolism. That same human aged 18 was likely thin, didn't have type 2 diabetes, didn't have Nash, and didn't have fatty liver. And so what we're talking about is not treating any one of those individual diseases, but by restoring youthful function to metabolism, all of those diseases get dealt with collectively. So the person loses weight, and the other 3 diseases go away as well. And then they then live a longer life, 10 to 20% longer, by having that famine pathway stress activated on a long-term basis. What this compound is actually doing is making the energy exchange very inefficient. So it'd be like a hydro dam wall having one pipe powering a turbine. If you then punch 10 holes in that dam wall, and those holes were not connected to the turbine, the dam would become very inefficient, and a lot of water would move through that dam wall to create the same amount of energy. So we're doing the same sort of thing. The mitochondria is your body's battery, energy pack, and we're punching pH self-limiting holes in that wall to change the hydrogen gradient, which makes the energy exchange very inefficient. Essentially makes you burn a lot more energy than you normally would. So that's the first program we're working on. That's actually the closest to market. We should have this in humans next year. The second program is CMA, chaperone-mediated autophagy. And so what this is, so every day your cells create waste. And every day your body recycles the junk out of the cells through a process called autophagy. And as you age, this autophagy function weakens. It still performs, it just doesn't perform as well as it used to. And so your cells start to accumulate junk. And as you get older, more and more junk accumulates. And this is what leads to dementia, Parkinson's, Alzheimer's, etc., amongst other things. But that's the main disease state that is caused by the autophagy process aging and becoming less effective as you age. Anna Maria Curvey is a professor at Einstein University in New York. She's one of our scientists. She's the world leader in this space, and her work won a Nobel Prize 4 or 5 years ago. She has worked out how to restore youthful function to the autophagy process, and in doing so, she can prevent animals getting dementia even animals that were never susceptible to dementia still live 20% longer because their cells are junk-free. But there's a bunch of eye diseases that can be treated with this technology as well. So that's our second program. So those first two programs are both in the realm of healthspan and lifespan extension. And the third program, which I think is the most interesting one, but it's also the furthest away, is epigenetic reprogramming, which is age reversal. This is there's a little bit more detail on it here. So as I mentioned, this science made a front cover of Nature in December, and Nature is the world's leading scientific journal. So to have that, it is the ultimate form of peer review. So, you know, it's hard, I think, when you talk about this work, if you use terms like young and old and aging and age reversal, it can be a bit much to get your head around. A much better, and I think they're just unhelpful words that we've made up to explain a process we don't really understand. I think a much better way to think about this is various degrees of damage. So youth would be an absence of damage at the genome level. Aging is an accumulation of damage at the genome. And then advanced age is an excess of damage at the genome. And that's all it is. And so think about your genome like a CD that holds information, and your epigenome is the reader of that information. And if you scratch a CD and it gets scratches just through wear and tear, it becomes harder and harder for the reader to read the information. But the music's still there, it's just buried under scratches. If you could polish those scratches out of the CD, the reader could read the information again, and you could read the CD like it was new. That's a pretty good analogy for what's happening with the genome and the epigenome. The genome holds your cellular identity, the epigenome is the reader, and as you go through life and you accumulate damage at the genome, that damage acts as interference and your cells lose their identity. The epigenome can't read the information correctly, and they start to regenerate in ways that are not according to their original code. It's noise, essentially, and it's what we would recognize as aging. But we can now identify the damage at the genome, and we can remove it using 3 of the 4 Yakinama factors that control stem cells. And when you remove the damage, the cells can then be read correctly, and they can be read and expressed in the way that they're intended, which is lack of damage, and then they regenerate without damage, which is what you would call youth. So these aged cells can regenerate in an undamaged way and become young again, essentially. So we did this in a mouse's optic nerve. This image is the first image of genuine age reversal in a mammal. This was from Harvard 18 months ago. And what you're looking at is a control animal at the top and the crush nerve model with the genetic reprogramming on the bottom. So these 3 stars show you where the crush point happened. And if you can imagine, the eyeball is here on the right and the brain is over here on the left. And before we crushed the optic nerve, the whole thing looked like this. It was just all those nerves are bright yellow. Well, actually, we inject dye so you can see the nerves. They don't look like that naturally. But when you inject dye in a nerve that has not been crushed, the whole thing looks like this. It's just lit up like fire. We then crush it and it dies. And the whole thing looks like the top model. It all dies. We then reprogram the crush point using 3 of the 4 Yakinama factors, and we remove the damage. The nerve uncrushes. These nerves regrow. And this is, I think, 2 weeks into the crush, into the reprogramming. And if you fast forward 4 or 5 weeks, it's come back to life. And the mouse can see again. So the mouse goes blind because we crush its optic nerve, but then once we remove the crush point damage, it uncrushes and it can see again. This should work in spinal cord injury as well, we think. There's no reason why it shouldn't, at least fresh spinal cord injury. And we have some fairly new data out of Harvard showing this also works in age-related hearing loss. If we do this to the whole animal, it gets cancer, it goes back to stem cells and it dies. So we can't control it in the whole organism. But the optic nerve is a great place to play around this sort of tech because it's a contained system. So it doesn't corrupt the rest of the organism as easily as other parts of the body. But there's no reason why we can't work this out in a whole animal. It's just a matter of time. We think we can already do it in the ear. So the plan is to go into humans to treat glaucoma and macular degeneration. We should be entering phase 1 trials within 2 to 3 years. And once we get it working in the eye, we'll start moving to other parts of the body. And this would be an injection. I imagine you'd probably take once a year. But who knows what the future would look like? Potentially it's a tablet you take once, but at the moment it looks like an injection that you probably need to take every 12 months. in terms of just giving that damage away. So what else can I tell you? So I guess another interesting part about this whole aging space is that aging is not recognized as a disease by any country in the world yet. The World Health Organization currently recognizes aging as a disease. It gave it a disease classification code 18 months ago, but no country yet does. But I think it's just a matter of time. I think just as obesity was not recognized as a disease 10 years ago, it is now. I think you'll see aging will also be recognized as a disease soon. It wasn't treatable before, and so you couldn't measure an impact on aging, but you can now, which is why I feel confident we'll be able to classify it as a disease soon. And I think governments are going to need this change to happen. You know, I think everyone's well aware of the underfunded state our healthcare systems are in. NHS is underfunded, Medicare is underfunded, global healthcare systems are underfunded. For the first time in our species history, the number of 5-year-olds is less than the number of 25-year-olds. Sorry, the number of 5-year-olds is less than the number of 65-year-olds. If you fast forward 20 years, that 25-year-old tax base is now supporting an 85-year-old aging population. That inverted pyramid is going to collapse on itself. And if you consider that 95% of your healthcare spend in your lifetime will be in your last 3 years of your life fighting age disease, we can now remove that entire spend. That's 95% of global healthcare budgets we can free up for tax reform. So governments are going to have to make this change. It's the only thing that's going to save their failing healthcare systems. But whilst it's not a disease, we can't make drugs for aging. We are making drugs for aging, we just can't call them drugs for aging. So we're making drugs for downstream symptoms of aging. And so you'll be treated for, say, Nash, but you're really getting treated for aging. And there'll be all these cross benefits that spill over into other disease states. So it's a really interesting time to be pushing into this space. And I think you're going to see a lot of changes coming through as these definition changes take place and as the science gets more advanced. That is the end of my presentation. Kate, do you want to hand over to you for questions?
Yeah, sorry, I was just clicking back on. It was taking a little bit of time. Thanks, Tristan. I think that's it's very fascinating stuff and gives us a great place to start opening up the discussion. I think if I can just put a call out to people who are listening to remind them that you can use the Q&A function. You'll see that some people are already putting in some questions now. So just a reminder to everyone that you can use the Q&A function. But whilst people are having a little think about that, I wondered, Tristan, if we can just start with a broad open question around what sort of motivated you to get into this space in the first place. It's a very fascinating and dynamic, and you might think, from not really that far ago, think it really sort of in the category of the sort of the space age, but actually, as with the space age, is actually happening, and it's now. What got you fired up about getting into addressing aging?
Yeah, it's a good question. I'm not totally sure, to be honest, Kate. It's something I have been thinking about, front of mind and back of mind, for 20 years now. The whole thing has just fascinated me for as long as I can remember. I guess I would describe myself as an internal optimist in that I really do believe that anything is possible, like anything is possible. If there are rules that exist, there are rules that we can understand and control and change one day. And aging shouldn't be any different. And so I've been wanting to do this for a long time and kind of watching the space for a long time. But when I started doing it, I honestly thought I'd spend 7 to 10 years in the wilderness trying to raise awareness around longevity research. I wasn't expecting the space to take off as quickly as it did. But you're right, in the first couple of years of doing this, we spend at least half of our meetings with investors trying to explain to them that this was real science now and it wasn't science fiction. They should look at this properly and take these things seriously. And it took a while to kind of break down those walls of understanding. But it's a very different landscape now. I mean, the whole space is just taken off in the last 18 months.
Mm. And I guess it's inherent in your presentation and indeed your own background that this is a very competitive and IP-driven environment. It's sort of like the holy grail of health, right? Like if you can crack this, then someone's going to do quite well out of it. So there's both a sort of an ethical and a commercial element to this. How does that actually manifest itself in the public domain? I mean, is this a genuine sort of race amongst a sort of a group of competitors trying to get there first?
Well, yes, I guess is the answer. It is. We were fortunate enough that we started this at a time when there was no obvious commercial path to market. There was no way to define a liquidity event in the sort of time horizon that institutional investors would require. So we've got probably a 5-year head start on all other groups. And one of our biggest barriers to entry really is the IP that we have. It's not like AI or crypto where there's literally 10,000 experts on the planet you can go to for either one of those subject matters. There's no shortage of experts in those spaces. There's less than 20 people in the world who can do this sort of stuff. And we pulled most of them together at a time when we did it in a vacuum. No one else was trying.
I guess, one of the questions that we've got there coming thick and fast now, Tristan, so I was sort of reading questions at the same time as listening to you. But so Chris asked a question related to that kind of investment piece, which is, how do you go about determining the source of your funding? Chris is asking really a point of interest around what do funders want? What are they after more than anything else?
Yeah, and that's a good question. It depends on where you are on the risk curve. So, if you think about the funding model, starting with venture capital, angel investors, venture capital, moving to private equity, so still unlisted, and then from private equity moving into listed assets. And as you go up that risk curve, the profile changes, the risk reward changes, the amounts of money you need to raise get larger, but the returns become smaller. The risk becomes smaller as well. So in the early days around the angel Series A, it was really family offices that were looking at high net worth individuals. There's a huge intrinsic value to the subject matter here. We're not just making widgets. This is not just about financial return. I think, to be honest, I think all of our investors are very interested in the actual applications of what we're doing, rather not just the fiscal element. And so that enabled us to get a wider mandate from our investors to innovate and take a longer term view on what we were doing. We weren't as pressured to come up with short term liquidity events as a lot of early stage companies are with VC institutional money. But then as we progressed along the risk curve and we started to de-risk our assets and to show that we could treat many different areas of aging diseases and that these molecules had huge applications in healthcare, we started to get then, and as you start moving from preclinical discovery work into phase 1 trials, you need larger amounts of money, but you're less risky. You then start to attract institutional money. We have a couple of sovereign funds that have invested. We have a couple of biotech VCs that have invested. Because again, as an extension to question, Chris on our call is really asking around that, I guess that sort of intersection between scientific collaboration versus the monetization of research, which is a space that universities in particular are very familiar with. So trying to find the sort of the nexus between being ahead of the game, the investment that you need versus actually what's the public benefit and public good and the extent to which the investment between those two things come. So I guess it's how much people are pursuing the research. And you talked about the collaborators you've got, Harvard and various others beside. How much is this around closed environment work versus open access public benefit stuff? But that's the territory that higher education is in across the world. Yeah, I think ultimately, at least from the private sector driven funding, it really comes down to commercializing assets. And so with each of our aging molecules, although we're targeting aging, because aging is not recognized as a disease state, we need to make drugs for symptoms of aging. And the first example I gave, the mitochondrial uncoupler, although we think it will be the world's first genuine obesity pill, that's not what we're interested in. We're interested in longevity. That just happens to be the mechanism. Obesity is such a hard indication to go for. If you made that your lead indication, it would take probably 8 years to try and get that through the FDA. Whereas Nash has such a large unmet need. It has more orphan disease status. So you can spend maybe 2 years with the FDA on Nash. And once you show that it's safe and that it works in humans and it has efficacy, the doctors prescribing it for Nash will see their patients are also losing weight, don't have type 2 diabetes anymore, don't have fatty liver anymore. And over a long enough period of time, they'll see that they're living longer as well. And so I'll just start off-labeling these drugs into other areas of application. Now, let me give you a quick fire question, only because somebody's asked, and I'm sure if one person's asked, others have. Lots of people are curious about what is Nash. So you talked about various diseases, but you talked about Nash. NASH is non-alcoholic steatohepatitis. It's when fat, so your liver tissue becomes unhealthy. Fat basically comes in and makes the liver unhealthy. It's a disease that happens as you get older, particularly around excess weight. So often NASH, fatty liver, type 2 diabetes, they'll all come as you get older and put more weight on.
Thank you. Now, this is an interesting question, been asked anonymously. So somebody's interested in whether we're going to end up looking like 120, age 120, or will the effects of reversive aging mean that we will look more youthful? Asking for a friend, exclamation mark.
No, well, so there are two paths to longevity research. One is extending health span, where you do still age, you just age in a very healthy way. And we think that, based on our animal models, we think that the hard limit for that sort of longevity is probably 120. We don't know, but that's what we think. And at that point, we just think that the mitochondria just gets exhausted and your body can't go on. So you will get to be 120 and you will look like a 120-year-old, but you'll be a very, very healthy looking 120-year-old. Like no inflammation, like no issues, nothing going wrong. But the epigenetic reprogramming, the actual age reversal, which really is just removing damage. If you remove damage, your cells regenerate. So whatever you looked like when you were 25 to 30, I guess that's an undamaged window of a fully grown human. That's what you would revert to. How your cells express themselves when you were 25 to 30 years old, that's your cellular natural state without damage. And if you remove damage, that's what you go back to. So it won't be a case of looking like you were 25. You'll become that way again.
And so I guess, like, I suppose at a broad level, that answers the question from Chris, who says, what are the limits to human aging? So I think that's probably, it's either a sort of unanswerable question or, within the context of what you said, we're talking about sort of 120 years, and it depends on what damage reversal you can do. So
no, I think the limits on human aging today are 120. Well, I say 120. You always have outliers.
Yeah.
It's less than 150. I'm sure of that. But within 20 years, I don't think there'll be any limits to human aging. If we can remain in an undamaged state, what's going to stop? You're going to ski into a tree or get hit by a bus. That'll be it. So you become amortal. You won't be immortal. You can still die, but you won't be dying from it.
So perhaps this isn't your space, but it does beg the question, which has come up a couple of times on the questions, really. I guess there's a sort of a moral, or at least an ethical question around, does that matter? I mean, so the fact that we can do that, should we pursue that goal? Because there are both positive but also negative consequences to solving the question of aging, right? So do you, in your work, spend any time on that kind of ethical space, or you leave that to others?
Look, we do, just from the point of view of it's front and center of everything that we're working on, and it's hard to avoid those questions, and it's hard not to think about those questions. But it's certainly not within our mandate to try and answer those questions. Science will just push the envelope of what it does, and as it creates things, then governments and regulatory bodies have to step in and work out how to best use that science. So that's very much in the realm of government policy. But if you just take a step back and think about what we're talking about removing aging diseases. And I don't think there'd be a single person in this call who hasn't at some point in their life taken antibiotics. Everyone would have been dead before 50, before antibiotics were around. There's any number of medical interventions that we all embark on to try and extend our health span as much as possible. This is just an extension of that idea. So it's really just removing things that go wrong.
Yes, I guess we, as much as we solve, a whole set of health economic issues with that, then I guess it raises then a whole mass of others, not least of which would be things around population control, which is something we already have. Like, if there's no limit, what does that mean for birth control, and what does actually the planet need? I'm not sure that we've actually even answered that question at the moment. We haven't considered what does the planet need. We've obviously already overdone on that. So it's it's a massive area of consideration, and I take your point that you're solving problems. It's perhaps not a disinterested perspective, but it's for others to then determine, well, what do we do with that new science, as indeed we do with lots of other things.
And there will be a huge burden on the planet with such an exponential increase in population. But there's a few things to say to that. Firstly, the planet's going to be fine no matter what happens. It's our species we need to worry about, not the planet. The planet will always be okay. And if we don't work out what to do with this technology, then Mother Nature will find a way. I mean, COVID's already shown us what happens when we push ourselves too hard and go unchecked. So there'll be natural checks and balances in place to cull our population if we don't work it out ourselves. But another interesting point, I think, around this sort of development is one of the things that makes our species so interesting is the ability to pass on knowledge. And now we're facing the possibility where we don't need to pass on knowledge anymore. The knowledge never goes away. So, I mean, imagine if Galileo and Einstein were still here, and then you had the future generations of innovators coming through. There's no longer a need to just keep recycling previous geniuses with tomorrow's geniuses. We just have this exponential growth of grey matter. I mean, that's an exciting idea, I think.
Yeah. Look, I'm interested. There's a question here from Janet Lim, who's really asking a question around the extent to which different cultures approach aging healthcare. So in particular in the Oriental medicine space, whether that has any bearing on the science that you pursue. So how different cultures approach aging already, and the impact that has on the approaches that you're taking with your group. Only
through the lens, I guess, of regulatory approval. So there are some jurisdictions that have more favourable, I guess, processes and barriers around getting certain things approved. We're really interested in taking these drugs through the FDA and the TGA in Australia and all the other major bodies. But if there are some areas that are a bit niche, we can go to certain jurisdictions to, I guess, accelerate those drug development programs. I think the only other thing I would say is that different cultures have different longevity bell curves. Japan is up there, it's one of the best, as is Singapore. And the one thing we do know, like the best way that anyone can impact their own age, regardless of their age, the best way anyone can impact their own health span and lifespan is through exercise. Diet's important, but exercise even more so. Like the actual activity of exercise regenerates the cells and activates longevity pathways. And so I guess cultures that have a more cardio kind of mindset should be those that are living longer. And we've found with these molecules that 1 + 1 = 4. So if you're taking longevity molecules, but you lead a fairly passive life, it'll still help. If you exercise without molecules, it'll help. If you exercise and take the molecules, it helps a lot. So I think active societies with this sort of intervention will see the most benefit.
I think there's a question that's in my mind, at least, a sort of an extension, a related question, which Julie Rimes is asking, which is about the affordability. So in any new developments, and particularly where there's sort of commercial application, the question Julie's asking really is around affordability, and again, whether there are going to be different jurisdictions who have access to this thing because they're in environments where they can afford to take advantage of the science that becomes available.
Right. Well, I don't see, we get asked that question a lot, actually. And ultimately, we won't be controlling the pricing of these things if we are indeed a company that ends up producing these sorts of drugs. Usually pharmaceutical companies come in and take over and run those programs from the biotech companies. The biotechs act more as the R&D engine, and the pharmaceutical companies act really more as the distributor of the technology. But there's no reason why this shouldn't be like penicillin. Like, this should be as affordable and as accessible as antibiotics. There's no reason why it shouldn't be. It will be supply and demand, and it'll be government policy. It won't be the cost of raw materials. So If everyone involved is a good actor and things go the way that they should, there should be something that's for everybody.
Yeah. Sorry, I'm just scrolling down because a bunch more questions have just pinged in here. Another question around, I think you've talked a little bit about this, but perhaps you could expand a bit more about the sort of the length of time that's likely to be required to validate your methodology and establish some cases. So there's obviously some exciting stuff happening. You've talked about your sort of mice trials in the last couple of years have been very successful. So that brings things pretty close in some parts of the work you're doing.
Yeah. So for the first program, the mitochondrial uncoupler, that will be in humans next year, doing phase 1 trials. So phase 1 is efficacy. Phase 1 is toxicity. Is it safe? It doesn't measure efficacy. Phase 2 is efficacy on a small n, and then phase 3 is efficacy on a much larger n. But with the mitochondrial uncoupler, because of its method of action, we'll be able to see efficacy in the phase 1 trial. It won't just be toxicity we'll be testing. We'll be able to see patients losing weight. So that's going to be in humans soon. The epigenetic reprogramming, in terms of like making an old human young again, like I can't tell you when that would be. My best guess is 15 to 20 years. But we should have that in human eyes within 3 years for phase 1, within 5 years to treat patients with glaucoma or macular degeneration. I think starting with patients who are blind from age-related vision loss. If it's blindness you were born with, we can't help. We can only help undo things that were caused by aging. So if it's age-related vision loss and the patient is blind, then there's not a lot of downside to taking an injection and a vector in the eyeball, especially if you think it can restore eyesight. So that's an example of an orphan disease state where you can move a lot faster because the benefits outweigh the risk of injury, materially. Did I answer the question?
Yeah, I think so.
Okay.
Somebody's asked a question, can you reverse the effect of a stroke?
That's a good question. I don't know. That's a really good question. Look, I don't know is the honest answer.
It's a big one, isn't it? Like everyone would love to know the answer to that.
Yeah, and I don't know, so I'm just guessing. But if I had to guess, I guess it'd be possible because at the end of the day, you're removing damage. We're talking about removing damage, and damage can be temporary or permanent. But I think all damage can be removed. So I don't see why that wouldn't be possible, but I'm not sure.
And so another question is coming around whether you're doing any funding or your research will sort of lead to possible interventions about increasing reproduction beyond the current age span.
Yeah, actually, we already have some about this. Is the tech out of UNSW in Sydney. We can restore, we can grow new eggs. This idea that women are born with a set number of eggs isn't true. We can wipe the ovarian reserve clean and grow new eggs. We can take aged eggs and make them young again, but better than that, just grow new eggs. Now, this is not an area of focus for us. We're focusing on other things. But if you think about reproduction, the male can reproduce in theory indefinitely. There's no real age barrier to male reproduction in theory. The female can also, except for the oocyte. It's just the egg that ages. There's nothing else that ages with the reproductive system. And so if you can keep the eggs young or make new young eggs, there's no real limit to when fertility has to end. Like I said, we're not pursuing those technologies. And they're not even, it's not even fertility drugs. They're actually aging drugs. It just so happens that the oocyte is the first cell to respond to restoration, which I guess makes sense. If you go in the other direction, if a female has to receive chemotherapy, the first cell that dies is the egg. It has to be protected from corruption, so it goes straight away. It's like napalm. And so if you go in the other direction and start restoring cells, the cells that are most receptive to restoration are the oocytes. So yeah, I mean, and this is not even with age reversal. This is just even in humans that are still aging, we can restore fertility. But with age reversal, I mean, people are going to live multiple lives in one life.
Julianne asked a question which I think tips back into the kind of, well, somewhere between an ethical debate versus kind of government policy ultimately, but around the fact that we are going to move to a place where, you know, our how we address aging is going to change quite profoundly. I think what Julianne's really asking is, but not everybody might want that. Like, does everybody actually like and want the idea of living to 120 or whatever it might be? And so is really asking a question around the extent to which any of this is personal choice, or whether simply the march of science means that, or whether we like it or not, that is the direction that we're going to end up going in. She's not asked this, but I guess by extension, I'm thinking around, you know, very topical debate around, you know, the right to die and personal choice around that kind of stuff. And all the ethical questions that raises kind of comes to the fore, doesn't it?
Yeah, no, it's a fascinating area to think about. And again, I think it depends on which of those two branches you're referring to. They're different answers. So maybe start with the first one, aging in a healthy way to 120, then stopping. I can't imagine anybody who would want to suffer dementia or cancer or cardiovascular disease, any of those aging diseases, inflammation, arthritis, frailty. These are all things that can be avoided now. And so it's not a case of living old in a bad way for longer. It's the opposite of that. You can live from 80 to 88 in a terrible state, or you can live from 80 to 120 in perfect health with no pain and no restrictions. So that's one stream. And that is personal choice, but I suspect almost everybody will choose to live a pain-free existence. Age reversal is different again, and I guess that is obviously a personal choice. But you may find people want to experience everything, and so they might want to get to 120 and then go back to 25 and then go to 80 and then go back to 30 and then go to 120 again and think, you know what, I'm done now, or not. You can do whatever you want with this in theory. But I was asked on a panel once what I thought the optimal age for a human was. And I was the last panelist to answer. And for some reason, the other panelists all seemed to gravitate around 150. I'm not sure why. They all had a different reason to get to that number, but that was the number they all kind of gravitated around. But I answered the question a little differently. And I said, if the technology exists that can remove damage and make you the way you were when you were 25, when I was 25, there wasn't a single day when I wanted it to end. So if I'm feeling that way every day, then I can't imagine ever being at a point where I want it to be over. It's not like a person who's 90 who's been living the last 15 years in pain. It's like you were when you were 25. There's no reason really for it to stop.
Tristan, I want to take advantage of a question that's come in from James Vickers, and I don't know if you know James. He's the director of the Wicking Centre for Dementia at the University of Tasmania, and he says that you know, there are diseases associated with, but not caused by aging, such as Alzheimer's disease. Increased longevity is already leading to an explosion of dementia cases. It's something that's very close to our heart here at UTAS and indeed across Tasmania. It's an estimated 1 million Australians by 2050 going to be affected by dementia. And so how do you tackle a disease process at the same time as increasing lifespan?
That's a good question. So you can't increase lifespan without increasing health span. We can't make animals live longer without making them healthier. So the health comes before the life. The health span extension comes first. There is no lifespan extension without health span extension. And Alzheimer's is a good case study because out of the 3 programs we have, one of the programs treats dementia. We were published in Cell, which is another one of the world's leading scientific journals. Anna Maria Curve at Einstein University, world leader in autophagy, was published in Cell showing that we can now treat dementia by making brain cells young again, by removing the folded proteins from the cells. And so, again, if you use those 2 different streams of aging, on the one hand, you're growing older in a healthy way. And if one of those ways is by restoring the autophagy process and removing junk from the cells, including the brain cells, yes, you're still growing older, but you're now growing older with junk-free cells. And one of the main aging diseases that gets rid of is dementia. But then the other aging stream of reversing age, if you reverse age, there aren't any humans I know of age 20 who have dementia. So that's the paradigm you're looking at.
Thank you. Now, this is going to reveal my my ignorance, but there's a couple of questions that have come in that are around. I don't even know how to say this, but the acronym is CRISPR. So,
CRISPR.
thank you. Right. So, question around: is there any research into gene editing and addressing this at the embryo level for any future babies born? And someone also asking around the difference between that acronym again and genetic reprogramming.
Yeah, okay. So I'll answer the second question first because I think it probably answers the first question too.
Yeah.
So CRISPR is gene editing. That's not what we do. That is changing your genome. So the applications it's supposed to have really are around rare diseases. And so if you have a genetic mutation that causes a particular genetic disorder, CRISPR can remove that from your genome before you're born, and the baby won't be born with that genetic disorder. That's what it's supposed to be used for, but in theory it can be used for anything. It can change your hair color, change your eye color. It changes how you are in some way by editing your genes and making them different. So that's not what we're talking about with our company. Genetic reprogramming is making you the way you used to be. So CRISPR is changing how you are. Genetic reprogramming is making you back to how you used to be by removing damage from the genome.
Thank you. Now, Tristan, I'm conscious that we're getting quite close to the end and we have a couple of minutes to wrap up things. So if you don't mind, I think there's a few questions which probably could be answered in a relatively quick fire way, or at least we can give it a go.
Okay.
So first of all, let's just see if I can do this quick. Right, so Peggy asks, what do you think of fasting to decrease diabetes and heart problems and other cancers, etc.? Not sure if this is your space, but perhaps you have a view.
Yeah, fasting is a great way to reduce those things. And in fact, if I was diagnosed with cancer, the first thing I would do would be remove all sugar from my diet. Glucose feeds cancer. Fasting extends health span, activates stress pathways. Exercise is even better, but fasting and exercise is a great way to increase health span and to help slow down certain diseases.
Okay. Next one, this is going to come across as quite an eclectic bunch of things. So how do you see lifespan extension impacting retirement age? So like, given what you said, might we all be working at 100? The idea sounds horrific, I have to say, but you know, that's kind of what you're talking about, right?
Well, again, there's two streams. So if you're talking about growing older, healthier, but still growing old, then yeah, it has to increase the retirement age. I mean, if you're now 90, but you have the body of a 50-year-old, no inflammation, no joint stiffness, no arthritis, no memory, cognitive issues. Again, at some point in the past, the average retirement age was not 65. That's a fairly modern development. So these things will always push forward as health span increases. But then talking about age reversal, back to my earlier point, if like when I was 25, I'd never felt exhausted. Like I never felt like I had to have a 10-year break. So if you're constantly in that state of youthful lack of damage, I don't know. I think the society is going to be very different.
Rob is asking, cartilage would stay the same, right? So large nose and ears, right?
Huh. No one's ever asked that question before.
Hey, well done, Rob.
Yeah, well done, Rob. I'm gonna have a go at answering it. I don't know if this is gonna be the right answer. So cartilage accumulates with age, noses and ears get bigger. I would have to think we're talking about complete reversal of if that is classified as damage. Anything, from what I've seen and what I've been told, everything's going to restore back to the way you were in an undamaged state. So I think an excess of cartilage would fall under the definition of damage and would be removed.
All right. And Grace says, can we take the treatment at any age for any group? And I guess you've kind of previously answered that. Well, it depends what damage you're starting with in the first place, right?
You can. It shouldn't matter. The older you are, the more damage there is. It might take longer, but in theory, it shouldn't make any difference. There shouldn't be a delay.
Okay, so you'll probably like this one. Are you looking for investment?
Yes, We're a biotech company. We're always looking for investment. So,
yeah, his details are on the back, so I'm definitely talk to Tristan. I'm sure he'd love to hear from you. And then there's a question around, do you have a publication, access to further information and so forth? And I guess, again, they just need to go to your website, and everything that's actually publicly available would be there, right, Tristan?
Actually, if you go to the Life Biosciences website, at the back there's publications. We've got a bunch of publications, press releases, etc. There's some TED Talks there. You can start going down rabbit holes of TED Talks, both with our scientists and other scientists as well. Yeah, there's a whole lot of stuff on YouTube, not just our company, but you'll start to see the ones that are interesting and they're all kind of linked to each other.
Tristan, look, we're out of time. There were a couple more questions, but I think we did a pretty good job of getting through most of them. But really appreciate your time, particularly the hour that you're speaking to us from. Very fascinating and topical subject. So thank you for your time. And particularly that because it wraps up our Explore program for 2021. So it's been a really great one to end on, giving people, I think, lots of, well, certainly lots to think about, but also lots of hope. So that seems a good place to end our series this year. And so whilst we can't all do this out loud, I know that everyone on the call will be quietly giving you a clap and saying thank you so much for the time and interest that you've given us today. We will be putting the presentation up on YouTube. It goes up pretty quickly, so certainly within a day or two. And we send that link to you directly. So for those who are on the call, you'll get that. And indeed, people who previously registered and perhaps couldn't make it after all today, that talk will be available. And I think you will see the information on your screen as I speak. You could, that's it, there it is. You can see where you can get the information from. So the next time that our alums will be gathering is on the online annual alumni meeting. We do encourage you all to attend. So that will, as I say, be online on Wednesday, the 24th of November. Our guest speaker will be the Vice Chancellor, Professor Rufus Black, and he really enjoys the opportunity to give a very open and frank and transparent talk around the state of the university, the issues that are facing the university, Tasmania, the sector, and is always very open and accessible to any questions which our alumni community might have of him, or indeed more widely for the university. So I do encourage you to make a note of that. Wednesday, the 24th of November is the next chance for you to join us online. But we do encourage you to think of topics that really interest you. All of our talks that we've put on are driven by our alumni and the interest that you have. We do know that health is a popular topic, so please fire away if you've got more topics, but if there are other wider ranging areas of interest, please do drop a line to the team, and we'd be really happy to put that into our thinking caps ready for next year. But for now, thank you once again to Tristan. Thanks to the alumni team for bringing this seminar. Thanks for your time, and have a very good rest of day, wherever you may be.